Everything around us, from a massive bridge to the tiny little components inside your phone, has a breaking point. Now, for centuries, engineers have been trying to predict that exact moment of failure. But now, AI is stepping in, and it's completely changing the game. So let's just start with the big question, right? Can AI actually predict when a bridge will break? I mean, that's about as high stakes as it gets. And it really gets to the heart of what we're talking about today. See, being able to predict this stuff isn't just some academic puzzle. It's about safety, it's about efficiency, and it's about building things we've literally only ever dreamed of. Figuring out how a structure is going to act under stress, well, that has always been one of the biggest challenges in engineering. For a really long time, we've had some pretty trusted methods, but as we're about to see, they kind of have their limits. Okay, so on one side, you've got your traditional formulas, and look, they're fantastic for simple, predictable shapes in a lab, but the real world, it's messy. It's full of weirdly shaped materials, unpredictable weather, all these factors that those nice, clean formulas just can't handle. And that's exactly where the old methods start to fall apart. And this is where AI comes into the picture. Instead of trying to write one single perfect formula that accounts for everything, which is basically impossible, we can use machine learning. It helps us find the hidden patterns inside all that real-world chaos, giving us a totally new way to look at the problem. So here's the key thing to understand about machine learning, or ML. It totally flips the script. Instead of us programming a computer with the laws of physics, we just show it a ton of data. We give it thousands of real-world examples of things bending and deforming, and the AI model figures out the rules all by itself. It's a data-first approach, not a formula-first one. So how does this actually work? Well, you feed the model some key inputs, things like how much load is being applied, what the material is made of, and the object's geometry. The ML model, which is often what's called an artificial neural network, kind of like a digital brain, then just learns the incredibly complex relationships between all those inputs to predict the final result, how much it's going to bend. And hey, this isn't just theory. There was a 2021 study by Lai that showed an AI-based method actually cut down on unwanted deformation during manufacturing by 3.5%. Now, I know 3.5% might not sound like a huge number, but in the world of high-precision engineering, that is a massive improvement. It means better products and way less wasted material. And the applications for this are just so broad. We're seeing these same ideas being used in enormous civil engineering projects. A study from 2023, for example, used machine learning to predict how much the walls of a super deep excavation would shift and bend, taking into account all the crazy complexities of the soil. It just goes to show you how adaptable this tech really is. Okay, so machine learning is really powerful. But what happens when the problem is even more complicated, with tons and tons of factors all interacting at once? For that, engineers are bringing out the big guns, a more advanced version of ML called deep learning. I want you to think of deep learning like a series of increasingly smart filters. You put the raw data in at the top, the first layer might spot really simple things, like edges or textures. Then the next layer takes those simple features and combines them to learn more complex patterns. It just keeps building like this, layer after layer, until that final layer spits out a super accurate prediction that captures all these subtle details a simpler model would have totally missed. And this layered approach, it gives deep learning some serious superpowers. It absolutely crushes it with huge, complex data sets, and it's amazing at understanding those subtle, tricky interactions between variables. And maybe the best part is that it's robust, which means you can feed it messy, incomplete, real-world data, and it can still give you a reliable answer. But of course, none of this AI magic happens without one critical ingredient: data. You have to remember, these AI models are incredibly hungry for it, and the quality of their predictions is 100% dependent on the quality of the data you feed them. Garbage in, garbage out. So where does all this data even come from? Well, it's a mix. A huge chunk of it comes from computer simulations. Things like the finite element method, which is a fancy way of breaking down complex objects into tiny little pieces to analyze them. But you also get data from old-school physical experiments and from real-time sensors that are placed on actual structures. You combine all of that, and you get the rich data set the AI needs to learn. But here's the thing. It's not just about having a lot of data. It's about finding the right data. This is a process called feature extraction. For instance, a 2024 study by Zhang and their team was looking at these high-tech composite space mirrors. They didn't just dump all the raw data into the AI. They specifically pulled out features related to tiny misalignments in the angles of the composite layers, Why? Because they knew that was a critical factor for how the mirror would warp. That's the level of detail we're talking about here. Okay, so we've covered the basics of machine learning and deep learning. Now let's get to the fun part and see how this stuff is actually being put into practice in some really recent research. I mean, just take a look at this. It gives you a great snapshot of how diverse the applications are. You've got everything from Zhang's work on space mirrors to trans research in civil engineering, and even Ju's designs for teeny tiny actuators. The fields couldn't be more different, but the common thread is that they're all using AI to build smarter, faster, and way more accurate predictive models. So, after all that, what's the big takeaway? What does this all mean? Well, what we're seeing is a fundamental shift in how we solve one of the oldest problems in engineering. We're moving away from relying only on old school formulas and instead embracing this data-driven, super adaptable new approach. I think this quote from the source material just sums it all up perfectly. AI isn't just a small improvement here, it's a total transformation. It's letting us create these predictive frameworks that aren't just more accurate, but are also adaptable, meaning they can learn and adjust to new materials, new designs, and challenges we haven't even thought of yet. And that right there leads us to the final, really exciting question. If we can predict failure with this kind of accuracy, if we can model complexity in a way we never could before, what does that unlock? What kinds of structures, the ones previously thought to be too complex or too risky, what impossible things will we finally be able to design and build with confidence? It's going to be a very, very exciting future for engineering.